thank you for the introduction and invitation. So it's a great pleasure to give this tutorial to the TAMIDS community. So we prepared this tutorial for the KDD conference, and that was a 4-part tutorial. And I think today we are making it slower and trying to cover only 2 of the parts. And if this works well, we can do the other part later semester. So in this tutorial, we will talk about, I will talk about this graph neural networks, some basic stuff, motivation first. Then student Yao Chen will talk about self-supervised learning. There will be 2 parts. So each of these topics will be 2 parts. So this part will be self-supervised learning. This part will be explainability. So for each of these parts, there will be a lecture part. So they will talk about different methodology for doing that, and then there will be a hands-on part. So how can you make use of this our software library called Embedding to graphs or deep to implement this functionality. And of course, there will be a Q&A after each session. And if you have any questions in between, just let us know. Okay. So deep learning, I think started from images. So this success mainly come up paper 2012 to improve image classification accuracy, and then it's move on to other areas like then move on to speech and improve speech recognition a lot. And recently, we are now moved to NLP for in translation and BERT. I think you also know this. So what we are interested in is what happens if we have a more generic data type. For example, if you have graphs, so you can think about image as a special case of graph where each pixel is a node, and you will have this very regular connectivity between these nodes. And so in general, if we want to deal with, for example, generically, we want to deal with graphs. For example, if we have a social network here, so each person, for example, can be a node, and then there are relationships among these different individuals, and this can be naturally captured as well. And my team was pretty much all this molecular problem or quantum problem where you have a system. So this system consists of some nodes and connectivity. For example, if you are dealing with, for example, a molecule, so each node can be an atom. Then there are chemical bonds between the atoms. So this can be treated as a molecular graph, and this is slightly different with the regular graph. So in the sense that this there is a 3D geometry. For example, each atom can have a location in space, and there's a distance between pairs of nodes and their angle. So this geometry is very important. For example, if we are dealing with a drug molecule, so the 3D geometry is very important because the drug and the target work like a key and lock. So the 3D shape has to match. And in many cases, you also have this document network, etc. So in general, we are interested in a model with a system as a graph in certain things. So for example, if you have graph, these are the major tasks you can do. You can do node level prediction problem. So for example, you have a document network. Each node is document. You can predict the class of this document. This is essentially a node prediction problem. You can also have a graph level prediction problem. For example, if you have a drug molecule, so you want to predict a property of this drug. For example, if this drug can be used as an antibiotic or not. So essentially, so this, for example, can be a 2-class classification problem. Given a molecule, predict is yes or no. Okay. You can also do link prediction. For example, in social networks, you try to predict if there will be a link between the 2 individuals or not. And so these are the prediction problem, and then you can do generation. So for example, if you are dealing with a molecular problem, basically you want to study if you can generate a molecule that follows same distribution as a training molecule, but with certain desirable properties. For example, if I want to design a new drug that can have a certain property. So, so in many cases, we are also interested in explainability. So for example, if we predict a certain molecule, for example, can be used as antibiotics, the domain expert may want to know why and how can you make that prediction, which part of the input is most important for making that prediction. So today we will talk about two of the topics. So I will start with examples of a node classification. Here you have a graph. So each node here represents, for example, a paper, a document, and the links represent the citation. If this paper, for example, cited this paper, and we want to predict if this paper belongs to computer science, math, or chemistry. So this is our node prediction problem. And graph prediction problem is where you have, for example, you have a molecule like this, and it's represented as a molecular graph, and you want to predict the property of this molecule. For example, if this molecule is going to be toxic or not. And as mentioned, there will be also a link prediction problem. You try to predict if there will be a link between two of the nodes. So, okay, so let's move on to the graphs. So to represent the graph, usually we need two matrices. So graph can be represented by adjacency matrix and feature matrix. Where because here the adjacency, if you have a graph, for example, with 4 nodes, the adjacency matrix will be 4 by 4. So one indicates there is a connection between these two nodes, and the 0 says no. Okay. Then there is a feature matrix here. Each row represents a node, and so this is, and we assume that there is a feature that is associated with each of these nodes. Okay. So there is the fundamental challenge for dealing with graphs compared to, for example, with images, because of this permutation inverse problem. For example, if I have this graph, so and if I permute the order of this graph, actually the graph will remain same as long as this connectivity remains same. So, for example, if I have, for example, a permutation matrix, so this is a permutation matrix, and if you multiply, for example, the permutation matrix left of this feature matrix X, so this will exchange the rows of X. And at the same time, you multiply the same matrix, permutation matrix on the left and the transpose on the right. So this adjacency matrix, you get a new adjacency matrix, X prime and A prime. So intrinsically, the graph remains the same. You just permuted the order of the node. Connectivity or everything remains the same. So ideally, this representation should remain the same. If you apply any learning on this or X and A, and that will apply to X prime and A prime. So the representation should remain the same. So just a reminder, so if you have permutation matrix like this, so if you multiply on the left, so it will permute the rows. If you multiply on the right, it will permute the column. So if you do both, so it will permute the rows and columns at the same time. So for example, if we try to learn a graph level representation, so that is given graph, we just learn, for example, we learn a vector out of this graph. So based on what we just talked about, so if F is a function that map a graph to a representation X. So suppose F given the graph, the output will be a vector. So because of this permutation inverse property, so if you give X and A as input, so it should give this basically you get a representation. That representation should stay the same as if you give representation as a permuted one of X and A. That's because the graph itself is the same graph. So the representation should remain the same. The key here is any permutation match. But there is also another idea of equivariance. So for example, so the idea of inverse is related to if you have graph level prediction problem. So the representation for the entire graph will not change if you commute the node. And there is also another idea of equivariance. Basically means if you have a, for example, if you have a node level prediction problem. So yeah, so here F basically maps a graph to a node representation matrix. So F here take a graph as input and the output a matrix where each row corresponds to length representation for each of these nodes. So if you apply F here on the original graph, you learn representation. So that is equivalent to if you apply P transformation of the input, you learn representation, and then if you, that is equivalent to P is applied to each of the feature matrix or the output. Basically, if you try to learn a node level representation, if you permuted the node, the output you just permuted version of the representation you learned from the original graph. This is called the equivariance. Basically, if you change the input and learn a representation, then you should apply the same transformation on the output. That's equivalent because the representation should not change. It's just the order has been changed. Okay. So next, this is one very important property that they need to maintain throughout this networks. It's all these operations. So I will talk about the next graph neural networks and the partial. So this is the partially based on the lecture during my people. So here, so if you have an input, it's your input graph. So the typical way of doing this graph operation is basically you have an input. So there's an intermediate layer should be commutation equivalent. So this intermediate layer usually will not change unless you have pooling operation. So this intermediate layer usually will not change the graph structure. It only represents, it only change the node representation. Basically, this needs to be equivalent. In the sense that if you change the order of this node, the output representation should also be proportionally changed. Okay? And then, for example, if you are doing a graph prediction problem, then the last layer should be some kind of global pooling where you pull this node representation into a single vector. So that one should be representation invariant. Okay. So this is very similar to if you have a if you try to learn an image classifier. So the intermediate layers are more equal translation equivalent. So the convolution layer. So if you shift the input, so this convolution layer will have a shifted version of the output. So this is the equivalent to translation. And then there will be a final pooling layer. That layer is invariant, so that if you intermediate layer can be shifted, then you have pooling layer, the output will not change. So this is so this idea is achieved through some local functions you can see here. So suppose we have a node here xj. So the neighborhood of this j is defined as x. And this is x. Okay. So basically this is the matrix of features of the neighbor. Then we define a function. This function phi act on the current node and the neighbor feature matrix. As you can see here, if you so this is node level representation can be considered as you. So your input is a graph, so the output is a feature matrix. So basically, this can be written as you have this phi function applied on each of these neighbor. So x1 is the first node, then this is the node feature of the neighbor. Okay, so basically from this to this, so you apply a theta function to each node and the neighbor of the four nodes. Okay. So if you can see here, if this function is invariant, if theta is invariant, so this whole operation will be equivalent, right? Because if the input, if theta function is invariant to this matrix, the row permutation of this matrix, so this whole system, this whole layer will be equivalent if you, in the sense that if you commute the graph, the nodes of this graph, the output will be just the permuted version. Okay, so you have so this is a blueprint for the different tasks of graphs. So if you have an input and graph, you have some layers. So these layers usually will not change the topology, will not change the number of nodes, etc. But it will only change the node representation, node embedding, people call it. And if you are dealing with the node prediction problem, you simply have a readout function. This one basically will aggregate all these node representations into a single weight. So you can do average, you can do sum. And if you are dealing with this node prediction problem, you don't need to do that. You just take these node representations and stack a classifier on top of each of these node representations. If you are dealing with the graph prediction problem, you basically need a readout layer to read out this. And if you are dealing with the link predictions, most of the time you just need to, if you predict the link between I and J, you just need to take the representation from I and J's node, and if you have an edge feature, you need to just consider these three. So as I mentioned, so if the way to build this equivalent function f here is we do this and we use the same phi function that is permutation invariant. So if your phi function, if we share the same function, same phi function among all the nodes, and then if this function is invariant, is permutation invariant to rows of this matrix, then the whole system of this layer basically is equivalent. Okay. So that's the basic property we need to maintain throughout all this layer. So there, so you may wonder what kind of function can be used as a phi. So if we use the same phi and this phi is invariant to the permutation, then this function f will be permutation equivalent. Okay. So what are the ways to implement phi? So typically there are three different ways, but then I think this is just a rough way to characterize, but it's not like 0-1 classification. So we can do in sense of convolution, we can do sense of attention and a message path. So convolution is basically you remember the phi function will take for each node you will take feature of u and input, and also features of the neighbors of u, which we call fleet. Okay, these are the neighbors of u. So what you can do is this function can act, for example, will take the weighted summation of the feature vectors of node, and of course you can have a transformation here, psi and transformation here. Right. This you can just think about this phi as a linear projection, or just MLT, multi-layer projection. Okay. So you can see if you do this way, this is some kind of aggregation. For example, you can think about this as a summation, element-wise summation. So this you can see this function will be invariant to commutations of these XVs because it's just a summation. And the coefficient here, C is usually some kind of time-coded. For example, this C can be based on degree or not U and V. So it's not normally it's not learned. So this is the original DCM graph convolutional network. And you can also do attention. For example, is a graph attention network. So what you can do is still this is based on some aggregation of the node features of the neighbor, but there could be this coefficient could somehow be learned. So you can learn a coefficient, but this coefficient should depend on node features of U and V. For example, this is your node. So you want to say how much this will contribute to the hidden representation here. So there should be a weight, and this weight could be a function that depends on features of this and this. So this is some kind of attention. For example, this is essentially this node trying to attain this node, and there is a weight that is learned. Okay. So and the third one is message passing. So you can have a message. You can have a message that it passes from this node to this node, but the message itself will depend on node features of the two nodes. Again, this is not this is just more conceptual. You can see there's a lot of similarities between different nodes. And I believe this one is quite natural because the idea of attention is very natural in graph because the key of this convolution one is This is the earlier version where basically we try to simulate the convolution of images or graphs. Or images, basically it's a neighborhood aggregation, but the key simplicity of images because each neighbor has fixed number, each node has fixed number of neighbors, and there is order. So this one is top right, top left, etc. And if you apply a kernel, it's nicely captured all the same local neighbor, but this parameter can be shared. But on graphs, this is almost impossible because each node has different number of neighbors, and there is no order between neighbors. How can we deal with that? I think the idea is that we can still do a neighborhood aggregation, but this coefficient just cannot be learned. Just because there is no fixed number of neighbors and there is no order. Okay. This idea of attention is quite natural here, just because the idea of attention is these coefficients are learned automatically. It's not handcrafted, so it's not it's not a parameter that is learned in the training process. So, for example, if you want to pass a message from this to this, there is a coefficient, but this coefficient just depends on these two node figures. You basically learn the weights by learning the node representations. So that's why you don't need to be constrained that I have to stay with same number of neighbors. They have to be ordered. It doesn't matter. In training, you can have 2 neighbors. In prediction, you can have 5 neighbors because these coefficients are not learned. The learned is the representation. Then the coefficient is based on the representations. Yeah. So.
Based on your illustration, I assume the graph you talk about are directed. Is that right?
Well, I think most of the graphs we talk about are not direct.
So for undirected graph, you can just consider like there are directed edge, but
bi-direction.
Yeah.
So in your first picture, is CBE the same as CEB? If I have another direction, would they be the same? Say CBE or CBC the same? Is CBC the same as CCB?
It depends. So this coefficient can be defined in different ways. Some people just define this based on degree of these 2 nodes. Some say only depends on degree of one of these nodes. I think it depends on how you do.
How about the second picture? So is ABC the same as ACB?
For this one, I believe yes.
It is.
In general, this is some kind of attention. So if A attends to B, I think the coefficient is same as B attends to A. Usually this is symmetric.
Based on the math formula, the attentional setting is the general, and the other 2, convolutionary and the message passing, are the special case, right?
Yeah, I think you can think about that.
Okay.
Because this comes later, and I think this is more popular and more powerful. This is more commonly used. This is just the original one. This is more like this one. I don't think this is very natural. This is try to simulate the convolution of images, but the coefficient here is not learned. You just cannot learn because each node has a different number of neighbors. There is no other, so this cannot be basically shared.
Thank you.
Okay. I think that's all my part. So. So next, I think Yao-Chen will talk about the self-supervised learning, and there will be a handout part. Then Haya will talk about explainability, and Zhao will help with the handout part.
Yeah, so can you go back to the earlier slide?
Yeah.
So is the function A also learned? Is that also parameterized by a neural network and learned? I know that the phi and psi are parameterized by a neural network,
Yeah,
right?
this one is usually I do MLP, like neural network. For this one, it's more like attention. If you look at the attention, you can learn it, but I think what people have found out is that using some kind of, for example, inner product and normalize usually works better. But I think you can learn, but I think in practice, usually this normalized inner product works well. Okay. So I will send this on to okay.
Okay. So in order for the online audit, I see the pointer. If you can use the pointer actually not because even with the camera, and I think you cannot see the pointer very clearly. If it's not too much, we can do.
So Dr. Ji had just introduced how we can build a GN graph neural network. And in later, we're focusing on how can we learn such graph neural network. We know there are many parameters in the neural network. And besides the typical training where we have the input graphs and we have the labels, that's one way of learning that. There are some other ways to train that graph neural network. So that's what I'm going to talk about. It is the self-supervised learning of graph neural networks. So we'll start with some motivations, like we have some applications like in drug discovery. We want to train a neural network, and in most cases, if you want to develop a new drug, you have very limited labels for the property because we need to do experimental obtain of that labels, right? And it's very expensive or time consuming. So one example that we want to use this self-supervised learning is that we first train the graph neural network or pre-train the graph neural network on a very large amount unlabeled molecular graphs. And then we move to a smaller number of labeled graphs, where we have access to the labels. So that's the motivation of self-supervised learning. And basically, it means that we want to train the GNN models under self-supervision. So what's self-supervision? It just basically refers to some label or some supervision that we obtain from the data itself. So there are two simplest examples. One is that we use a portion of the graph data to predict the rest of the graph, which is also called the reconstruction of a graph. And there is a second example that so we have many portions of graphs, and we train the GNN to predict which two or whether two even portion of graphs are originally from the same graph. So that's basically two simple examples of self-supervision. And the self-supervised learning is actually very successful in the image domain and some NLP. For example, the BERT model, it is trained under self-supervision and it is fine-tuned on some specific tasks. And recently we see an explosion of also the self-supervised learning on graph neural networks. So it's also a very promising way of training graph neural networks in some specific scenarios. So basically how we can use those self-supervised learning exactly. So there are typically three paradigms of using self-supervised learning. There are the unsupervised representation learning, where we train an encoder to predict the representation, which is a vector of the graph or a node. And also we have the unsupervised pre-training and also the auxiliary learning. So both unsupervised representation learning and unsupervised pre-training are performed in two stages. So in stage one, both of them pre-train or train an encoder, GNN encoder with self-supervision or without label. And then for the unsupervised representation learning, we just use the representation we obtained from the encoder. Basically, we fix the encoder and we freeze the representation and use all those representations with a small portion of labels to train a linear model or some lightweight model to perform downstream tasks. So this setting is most common in the industry because they have very large scale graphs or they have very unbalanced labels. So and they have also multiple tasks on each graph or node. So what they do is they first learn some model to obtain the representation of each node, and then they can do whatever they want based on the representations. And the second paradigm, the unsupervised pre-training. So after we have trained the GNN encoder in the first stage, we need to further fine-tune the GNN encoder together with a prediction hat on some downstream tasks we're going to work on. So basically the encoder is still trained in the second stage. And this is, we have two examples that you might be familiar with. The first one is transfer learning, where we pre-train a neural network on some data set, and then we fine-tune it on some different data set. they can be like very different. Like we have some natural image and some medical image, or also in this like we have some molecular for task A, and we can transfer that to task B. And the second example is called the semi-supervised learning. So it's like we are given a large data set, but we only have label for like 1% or 10% of the instance in the data set. So what we do here is we first pre-train the data, pre-train the GN on the entire unlabeled entire data set without label. Then we go to the 1% of labeled data to do the fine tuning. That's basically two special cases of the unsupervised pre-training. And the third paradigm is called auxiliary training. It is basically a one-stage training. So here we train the neuron, the GN with both supervision and self-supervision, which means we use all the labels here, and we consider the self-supervised learning or objective as some kind of regularization that helps the model to generalize better to other unseen data or tasks. So that's how we can use the self-supervised learning. And now we are going to the method of self-supervised learning. So there are recent taxonomy basically consider two types of self-supervised learning. So they are called contrastive learning and predictive learning. So remember the two examples I mentioned in the previous slides. So in the case one, we can predict whether two portion of graph comes from the same graph, right? That's basically intuitively what contrastive learning do. So basically we have many pairs of data, and some are from the same graph, and some are not from the same graph. So basically we want the encoder, we want to train the encoder to discriminate whether this pair is from the same graph, or we call it a positive pair, or they are from different graph, and we call it a negative pair. And also in the second example, we said we can do prediction from a portion of the graph to the rest of the graph, or doing the reconstruction. That is an example of the predictive methods, so which is shown in the bottom. And yeah, so they're both theoretical. So the examples are just intuitive understanding. We also have some theoretical explanation or grounding for both of methods. So for a contrastive method, it can be explained or grounded by the theorem called mutual information maximization, which we want to maximize the mutual information between the two representations we learned, which is from the two different versions or two different parts of the graph. So, and recent work on the contrastive learning mainly focusing on how to generalize, like in the example, we're using two portions of graph, but we can generalize that. We can use two versions of the graph based on some different argumentations. So we have argumentation one that we obtain the version one, or we call it a view one of the graph. Like we randomly remove some edge or add some noise to the graph. And we use another different argumentation to the same graph, and we can obtain the second view. And what this do is that we have two views, and we want to maximize the mutual information. And actually, what a very difficult part is that how we can obtain the two views. So what argumentation is can help best on the learning of the network. That's the most focus on the contrastive learning researchers. And also we have the predictive model, and many of them are like heuristic or ad hoc based on ad hoc prediction tasks. And some of them can be expanded by some theorem called information bottleneck, which I will cover later. And basically they focus on how to design the pretext prediction task, like whether we are going to do reconstruction or we are going to predict some property of the graph based on the given data, like the number of k-hop neighbors, etc. Basically, how it only focus on how we design the objective for learning tasks. So here's an overview of all existing self-supervised learning methods on graph. So basically, we consider two categories: the contrastive one and predictive ones. And for contrastive ones, a specific method can be determined as long as we have specify is what objective it used and what view generation method we are using. And also for the predictive method, we further categorize them into like 4 sub-categorizations, like graph reconstruction, like for example, the graph autoencoder, and graph property prediction, like we obtain some statistical or some domain knowledge-based properties, like which it can be easily computed from the input data itself. And or we can also do self-training where we just randomly generate some pseudo labels to help the training. And also we have another categorization called invariance regularization, which we perform some regularization on the learned representations. Is also a self-supervised without label. So in the later talk, I will mainly focus on introducing the contrastive method, and I will also briefly go through the specific part, which is the invariance regularization part, more recently more promising. So okay, so for contrastive method, the key idea or intuition of the contrastive learning is that we want to learn some representation such that if the 2 graphs are very similar to each other, then we want their representation also to be similar or to close to each other. And also, if there are 2 dissimilar graphs, then we want the representation of the 2 graphs to be like far from each other. Yeah, but in practice, we do not have a ground truth of like what are similar graphs and what are dissimilar graphs. Okay? We do not have a well-defined measurement for that. So what we do here practically is that we do the argumentation on, we do different argumentation on some graphs. And if we have 2 argumented graphs that they are both from the same graph, like we have graph A and graph B, and we do 2 argumentations for each of the graph. If we take 2 argumented graph from the same graph, then we consider they are similar. And if the 2 argumented graphs are from different original graphs, then we call them dissimilar. So that's how we define the pairs of data in practice. And actually, they can be explained by the theorem grounding of mutual information maximization. So basically, here we consider a graph as a random variable. And then we consider the 2 argumented graphs as 2 views of the graph as another 2 random variable based on a given graph. And after we compute the representation of the individual view, we have another 2 random vectors, which are x and y. They correspond to the 2 views, right? And so here, what I do is that we want to maximize the mutual information between x and y. These are 2 vectors, 2 random vectors. And how we computed mutual information is that we maximize the KL divergence between the jointly sampled x and y and independently sampled x and y. So basically, here we consider if the x and y are jointly sampled, we consider them as a similar pair. Or if they are independently sampled, we consider them as a dissimilar pair. So then we can take a look back to the how we practically doing that, which is we perform 2 argumentations on the same graph. And if the 2 argumentations are from different graphs, because we first independently sample 2 different graphs and do argumentation individually, then we consider this pair as independently sampled. And if 2 argumentations are from the same graph, we can say that they are like jointly sampled because they comes from the same graph. So that's how we theoretically explain them. And yeah, so basically, if we want to specify a contrastive, yeah.
What kind of random variable are you using for representation of the graphs?
So the
Maybe
representations
normal?
are all vectors, right? So we just consider the 2 representation from 2 view as 2 random vectors.
So what kind of random vectors? Like a Gaussian, maybe?
We do not know what, actually, we do not care what exact distribution they are. We are learning their distribution that leads to the best performance. Yeah. So basically, if we want to specify a construction method, we only need to know that what view generation we are going to use and what GNN encoder we're going to use, like based on convolutional or attentional, and also what object for mutual information maximization. I will start with the objective first and going to the view generation. So because the mutual information, as you see, is very difficult to handle during because the computation of that is very heavy. And so practically, we usually use some estimation of the mutual information or some lower bounds of the mutual information to optimize. So there are two very common estimations. They are called the Json Shannon estimator and also InfoNCE. So you may find the formulation here very complicated, but I will give you an intuitive explanation. So for the Json Shannon estimator, it's basically like we're doing a binary classification of every pair of data, whether it is positive pair or a negative pair. So it's just we have many pairs and we do the binary classification for each pair of that. And for the InfoNCE, it's like that we have a batch of data, and we for each sample of the in the batch, we give them many candidates. Like only one is positive, only one is from the same graph at a given instance, and all the other are from different graph. So basically, what we do here, we are doing a multi-class classification, where I want to try to find the only one that comes from the same graph with the given data from the batch of data candidates. So the major difference here is whether we're doing a binary classification or a multi-class classification to select the positive pair and negative pair. Now we're going to the view generation part. So this is actually a very important part for constructive learning. And so basically there are some simple examples of how we can obtain the view generation views or argumentations. So as you can recall that we have introduced a graph. It's usually represented by two matrices, the adjacency matrix describing the connectivity in the graph, and we have a feature matrix that describes the node features, what the attributes of nodes. So we can do argumentations on either adjacency matrix or feature matrix or both. So basically we consider three types of argumentation: the feature space, where it is performed on the X, the feature matrix, and we have structure space transformation, which would perform on the edges or the connectivities. And also we can do some sampling based, where we select a subgraph from each graph as an argumentation. So for feature space, we can just randomly masking or add noise to the node feature. And for structure space, we can just randomly remove some edges or add new connection to some nodes. And also for the sampling based, we can do uniform sampling, and we can do some random mode based sampling, just different ways to obtain subgraphs. Yeah. And actually for graph, the argumentation of graph is actually very different from the performing argumentation on images. Because for example, if we have an image of dog, when we perform like rotation, cropping, or flipping, you can see semantically it's still a dog image, right? Because it doesn't change the meaning of the image. But for graph, we do not know the semantic of graph, right? So if we like remove some edge or remove some nodes, maybe the semantic of the graph like totally change. We don't know whether it's like what is semantic. So here we need some further theoretical guidance. So it's like to answer like what are the good views generation for graph. And there are a study like focusing on this. So basically optimal views, pair of views with V1 and V2 generated for constructive learning should satisfy two conditions. The first one is that we want the two views have their mutual information minimized. So like we want them to be as different as possible, but we need that to subject to that both argumentations should that missing any data, any information related to the downstream label. So we want the views to be different from the original data, but it should not change any information related to the label. Right? Otherwise, it will add some unwanted noise to the data. So basically, it means that we want the mutual information between the argumented graph and the label to be the same with the mutual information between the original data and the label. So that's a very important theoretical guidance. And many recent work that they're studying how do we generate views are based on this intuition. And for example, there are some like adversarial learned view generator that for the generator part, we want to minimize the mutual information. And for the contrastive learning part, we want to maximize the mutual information. That's a very interesting example. And that's all for the contrastive part. And we will also cover several very recent examples of the predictive learning part, specifically the invariance regularization. So you can see that their formulation is a little bit similar to the contrastive method. And the key difference is that we do not need any negative pair of graphs during the optimization or during the learning of those predictive methods. So for example, this is one of the most popular recent works called Mvgrl. It is adapted from another very famous work, which is BYOL, Bring Your Own Latent, which is for self-supervised learning for image data. So what I do is you can see they still have obtained two views of the given graph, but what their objective do is they just simply minimize the difference between the two representations for the two views, and they do not like contrast with negative pairs. And you may ask that potential problem here is that maybe that if we have a model that consistently predicting a vector, all zero vectors, right, for any given graph, then we will have a minimized difference as an objective. So to avoid such like trivial solutions, they simply use some additional tricks, like they stop gradient, do stop gradient. They do stop gradient on the second view, and they update the parameters here using some moving average way of that. So basically, they want to avoid to learn such trivial embeddings. And there are some other inverse regularization methods, which another one is called a Conical correlation analysis. And so their objective here, as you can see, they also include an invariance term. Basically means that we want to minimize the difference between the representation of the two individual views. And also to avoid the trivial solution to be learned, they also add a decorrelation term to here. So basically, you want to reduce the redundancy of both representations ZA and ZB here. And there's another recent work by us, which called the lab graph. So it also include, so basically, its objective include two terms. The first one is invariance regularization term, which means we still. So for this method, what we do is we also input two versions of the graph to the GNN, a original version and another version that we some nodes mask, and we input the two versions to the GNN and obtain two representation respectively. And the objective or loss computation consists of two parts. The first term is invariance regularization term that we want to minimize the difference between the two representation of the two graphs, right? And the second term is a reconstruction term, where we want to use the learned representation to reconstruct the connectivity of the original connectivity or the feature of the original graph. That will also make sure that no trivial solution will be learned. But you may find the formulation is very similar to previous methods. But actually, all these methods are derived from based on different theoretical groundings. So, for example, this log graph is based on the objective here is derived as self-supervised upper bound of supervised laws. So, but its formulation is very similar. So, and you may ask why. I will explain this in the next slide. So first we will, as a summarization, there are some similarity among the predicted, specifically the invariance regularization method. First, they do not require any negative pairs during training. And as a result, actually they have better scalability because they do not require very large number of batch sites because they do not need many negative samples. And also their objectives all include a term to regularize the difference.
When you say the better scalability, do you mean there is no cursor dimensionality or it's just the better?
I mean the scalability. So there is a drawback of constructive learning method because they need enough negative pairs. You need to input a very large number of samples to train the neural network at each iteration. So because of that, we need a very large batch size, and also the memory consumption is very large.
So you mean it's the dimension of the number of samples?
Yeah, the number of samples.
What about the dimension of the graphical data, the graph dimension?
I think for both methods, the dimension of graph is the same, should be the same. We can consider them as the same. So the data will be the same, but the difference is the training, how we train the model.
Okay. Thank you.
So basically, the construction method requires more sample and more memories. So here, an advantage of predictive method is that it requires less memory.
Actually, this is actually a really good point. My understanding is that the functions that you learn in a typical graph network, phi and psi, that we started in the beginning, they are completely independent of the number of nodes in the graph.
Yes,
right?
Yeah.
So the number of parameters that you have to learn is not at all dependent on the number of nodes in the graph.
Yeah, correct.
So what you're learning is not dependent on the dimension of the graph at all. So there is the scaling of the number of nodes has no relevance.
Yeah, the number of parameters is fixed as long as you have determined what GN you want to use. But we still, if we have a larger graph, we need to still compute some intermediate matrix, and it will consume more memories if you have a large input graph. But it's not comes from it's not because the parameter size, it's because the data set. Okay, we can discuss later if you have questions. So yeah, so actually you find the similarity between all these methods, and actually it can be their effectiveness can be justified the same theorem called the information bottleneck. So the information bottleneck theorem basically tells that a good representation should satisfy two properties. The first one is that the representation should contain as much information as possible from the original data. That's the first condition. And the second condition is that the representation should be invariant or should be robust to any noise on the input data. So if you recall all of this method, you can see that we use the invariance term to assure that the representation is robust to noise on the input. And also we have some different term like here the decorrelation term and the reconstruction term here to make the representation to be as informative as possible. So that's all the similarities among this method. And also there are for sure many differences. Like first, all the formulations of the entire objective are different because they are based on or derived from different theoretical groundings or insights, as I mentioned. And also they use practically, they use different technique to guarantee such informative representations. And that's all for the method part. Is there any other questions? The next we'll move to the demo part. So it will be better if you have already installed it, but it's optional. You're totally fine if you do not have the library or coding. We'll go through several examples to show you how to use that our library to prove self-supervised learning in many scenarios.
So in this hands-on tutorial, I will show how to reproduce and develop self-supervised learning methods using our EIG library. Specifically, I will show 3 application scenarios. First, I will show how to implement existing self-supervised learning methods, including several state-of-art methods. And then I will show how to develop and evaluate your own methods. Finally, I will also show how to extract embeddings generated by self-supervised learning methods. Let's see the first application scenario about how to implement existing methods. Here, I will show 3 examples: graph level unsupervised learning, nodal level unsupervised learning, and graph level semi-supervised learning. The graph level unsupervised learning aims to learn a good representation for the whole graph. And here, you firstly need to download a data set. Since we have already implemented the get dataset function, you just need to use our function from the EIG and define the name of dataset you want to try, and also define the task type, and then define the dimension of embeddings. Then use our pre-implemented encoder class and also method class. The encoder class, the input parameters include like dimension of feature, dimension of hidden dimension, and the number of layers, GN backbone type, and many other parameters. Here, for example, I want to use the Mvgrl method. I just need to use the pre-implemented method class. And the input parameters include dimension of graph level embedding and dimension of nodal level embeddings. And then I define encoder and the method following the setting of original paper like this. Then use our EIG evaluator that is specifically for the graph unsupervised learning. And set up the training configurations such as batch size, retraining learning rate, pre-training epoch numbers, and many others. Finally, perform the evaluation with the given method and also the corresponding encoder. Here, the results show the average accuracy and the standard deviation of multiple runs of the standard downstream tasks.
What your data set look like? A JSON matrix or?
The data set, first, the data X means the node feature. And you will also have the edge index provide you the relationship about
The
adjacent
edge
matrix.
index is like a sparse representation of the
Yeah.
adjacency matrix.
It's more efficient than adjacent
Oh.
matrix. Yeah. Okay. Yeah. If you want to reproduce another existing method, for example, Mvgrl, for the same data set, you need to follow the Mvgrl paper to define 2 encoders. Both encoders are sharing the same backbone and same activation, but the only difference is that the diffusion encoder uses edge weights to compute the aggregation, but adjacency encoder doesn't. And for the Mvgrl method, we also pre-implemented this one in our package. And the input parameters, in addition to the dimension of graph level embeddings and dimension of nodal level embeddings, it also includes the diffusion type. And you can also set the device number if you want to use GPU instead of CPU. And then use the evaluator and set up the training configurations and finally perform the evaluation. Note that here, the input of encoder could be a list
of encoders if you have more than one. The second example, node level unsupervised learning. It aims to learn node representations instead of graph representations. You also need to get the data set first, and then define the dimension of embedding and define the encoder and also the method following the original paper. Here, the example is the GRACE, the existing method. And then I will use the evaluator that is specifically for node level unsupervised learning, and also set up the training configurations and perform the evaluation. It's same as what I did before in first example. And the result here is the average accuracy and the standard deviation of multiple runs of a downstream node level task. The third example, semi-supervised learning. In semi-supervised learning, we use all the data without label, and we also use a small portion of data with labels. For semi-supervised learning, it's usually for graph level tasks. And here I will show one example using GraphCL method. You also need to get data set first and define the embedding and define encoder and the method. For GraphCL method, for the semi-supervised setting, we use Json as backbone. We have several different available options for view augmentations. And then we use an evaluator for semi-supervised learning to perform the evaluation. In addition to the standard evaluation, we can also do research. For example, here, I provide a list of pre-training learning rates and a list of pre-training epoch numbers, and the result of research gives me the best accuracy and standard deviation of the downstream task, and also the best combination of hyperparameters. In this way, we can select hyperparameters. Okay, so it's about the first scenario of implementing existing methods. Then in the second application scenario, I will show you how to develop your own method. For example, here, my own method named SSL model. It's a child class of our pre-implemented contrastive class. You can use it directly. And here I use the Json Shannon estimator as my objective, and use MLP projection head. And then I use the node mask for both augmented views, but you can choose many other options from our DIG library as you actually introduced. So it includes like edge perturbation, drop node, subgraph, many other options. And you can also implement your own function to build different augmented views. Okay, then download data set, define the dimension, define the encoder with specific structure, and also define my own method. Here, in this example, I use our DIG pre-implemented evaluator to evaluate my own method because our pre-implemented evaluation tool is very convenient to use, and our evaluator works with most data sets from PyTorch geometric. However, you might still want to try some specific special downstream tasks that are totally different from our standard downstream tasks. In that case, you might be more interested in the third application scenario, in which I will show how to extract graph embeddings generated by existing self-supervised learning methods. Here we use Mvgrl as an example. You define the encoder, define the self-supervised learning method, and also get the data set as we did before. But here you need to define a pre-trained data loader and as well as the optimizer for the pre-training. Then perform the pre-train with the given encoder and the pre-training data loader, optimizer, and other parameters. After the pre-training is done, you can use the encoder to get the dimension of, get the embedding of graphs in the data set. Here is the example of how to get the embedding of the first graph in the data set. And you can get use this way to get other graphs embeddings. And you can also get node embeddings, like following a similar example. And then you can apply the pre-trained embeddings to any other downstream tasks that you're interested in. Okay, so here's all about our code session for self-supervised learning module, and you can check our Jupyter notebook from the GitHub. Thank you.
Hello everyone. So previously, OG has introduced the block networks. And Shuiwang has talked about the self-supervised learning method in the block networks with unlabeled data. In this part, I will give you some instructions on the explainability of graph neural networks. When we already have a well-trained model, how to interpret this model, how the people can understand what the model think and why the model do such predictions. Graph neural networks have achieved great performance on many real-world tasks, such as node-level classification and graph-level classification. However, people usually take the graph networks as a black box. That's to say, we take graph as the input and take the final prediction as the output. But we don't know why the model gives such predictions. We don't understand the deep learning models. When the models fail to react as we think or make some wrong predictions, we can hardly figure it out. And we don't know why the model fails. And we will doubt this model. And this concern will cause some problem when we employ these models. So the explainability methods provide human intelligible explanations and help people to understand why the model do such predictions, to build the trustworthy AI to cooperate with machine learning model and human. Yeah. To build the explainability methods, there are several challenges that we have to face. The first challenge is to combine the age information in the graph-like data. For the image-like data, they are grid-like data, and for the text data, they are sequence-like data. However, for the graph data, they have age. The age information denotes the connection between different nodes, and such topology information is quite important when doing some prediction task on the graph-like data. So when we explain the graph neural networks, we have to consider such topology information. For each graph, we can consider it used based on two views. The first view is age-based view, and the second view is subgraph-based view. The age-based view gives importance score for each age in the input graph, and the subgraph-based view gives an importance score for each subgraph of the original graph. Compared to instance level, which is related to each input graph, the model level methods give you some high-level explanations. What graph patterns will lead to a certain behavior of model. And some model level methods such as XGN studies these problems. Yeah. And the second challenge is how to evaluate the explanation results. Once we have the explainability methods, how do we know these explainability methods give you a right explainability results? It's also a quite difficult problem. If we have some graph data like molecules, the explanation results can be a carbon and neutron rings or rings. And we are not experts in hardly understand why these explanatory results lead to certain molecular property predictions. So in order to provide human understandable explanation results, in our package, we provide sentiment graph datasets. And in this dataset, the explanation results is text terms that expressing the positive or negative opinions. For example, here, the final explanatory results can be a filmmaker has nothing fresh. This is obvious negative opinions. And in this way, we can easily verify whether your explanation results are correct or not. Instead of some visualization, we also want to have some quantitative matrix to compare different explainability methods systematically. Since different explainability methods are based on different techniques, and that we will introduce later, so they can hardly compare. Here we propose three metrics called fidelity plus, fidelity minus, and sparsity. We can combine them together to compare this method systematically. Here is the overview of existing explainability methods. We can split them into two branches. The first branch is the instant level explanation methods. This methods is input dependent. Given an input graph, these methods will tell you which graph components in this input graph will lead to the final prediction results. Based on different techniques, these methods are divided into 4 categories. The first category is the gradient and features-based methods. This method takes the back propagation gradients and forward activation features to approximate the importance score. If based on the assumption that if the graph components is important, then the back propagation gradients and the forward activation will be very large. And these methods are usually very famous on the image-like data. However, if you directly employ them on the graph-like data, it ignores the topology information, which is very important for the graph predictions. The second category is called perturbation-based method. This method will mask the input graphs and use the masked graph and the prediction of the masked graph to learn a graph mask generation algorithms. And then use these algorithms to find out which graph components is important. If the graph component is important, when this component is masked, then the final prediction score will drop a lot. For these methods, they usually take the graph neural networks as a function mapping from the input graph to the final prediction results. That's to say, they take the model as a function, and we can employ these methods on many different model architectures without pain. So this method is called model agnostic methods. The third category is called decomposition-based method. This method will propagate the importance score from the final prediction score to the input graph layer by layer. And you can track the importance score layer by layer to understand how the model gives us such a prediction. However, these methods have to design specific decomposition method propagation in different model architectures. So it's not model agnostic. We have to design specifically for different model architectures. And the final category is called surrogate-based methods. These methods will study a local region of input graph instead of just the input graph. It first samples a data set in the local region of an input graph, and then use the original graph neural networks to get the paired data as the data sets. Then it will use interpretable model such as linear model to learn the importance score on the generated data set. However, since the graph contains the topology information, it's very hard to define the local region of the input graph. It's very hard to define what topology is close to the original input graph topology. So these methods are still needs more research on these branches. Instead of instance level explanations, model level explanations provide higher level explanations. These methods such as XGN try to find the specific graph patterns that can lead to certain behavior of model predictions, such as maximizing the prediction score of a specific class. And then the generated graph pattern can be taken as the reason why the model think what the model think this class have. And that's the overview of the existing graph neural networks, existing explanation methods on the graph neural networks. And I will introduce two well-known methods, GN explainer and the subgraph estimator. When we explain the graph networks on the graphs, we can formulate them as an importance score assignment task. We can assign importance score on the edges. For the GN explainer, it will learn importance mask on each edge separately, and then take the edges with top K highest importance score as the final explanation results. Another way is to assign importance score on collected subgraphs. The subgraph X will first extract the subgraphs from the original graphs, and then calculate the importance score for each subgraphs. Since the searching space for the subgraph is much larger than the number of edges, so the subgraph X will take more time to find out the final explanation results. But since it gives the importance score for each subgraph, it considers the cooperation between different nodes in the subgraphs. How do you get that number on the 0.5, 0.7? Okay, we have some importance score assignment function. If we put the model and the subgraph into that function, and we can calculate the final importance score. And in subgraph X, we use the Shapley value, which comes from the cooperative game theory, to fairly assign the importance score to each subgraph.
How do you confirm the validity of those score assigned?
The validity.
You have your own standard. How do you ensure that this is a fair score assignment?
Yeah, this for the sharply value, it is called fair because it achieves 4 axioms. If one node or one subgraph have no contribution, then it will have 0, and if two subgraphs has the same contribution, they will have same values. And based on these 4 axioms, we call this score function field. As you see, the score value functions have some constraints to make the functions to assign the importance score field.
So do you study the importance score on every subgraph? Because like here you show an example of this simple subgraph. So that would be like if the graph is very large, then the computational complexity can be very large, right? So is that a problem?
Yeah, that is a problem. So to address this problem, we will use some heuristical search algorithm to cut the search space to find less subgraphs with highest importance scores. So I will introduce these 2 algorithms details. The first algorithm, GN Explainer, will give edge masks and node masks as the final explanation results. So in the figure A, for each edge, the GN Explainer will first assign an importance score from 0 to 1 to each edge, and then to explain the prediction results of target node V, we will optimize the edge masks using some target, and then the final explanation result will be the green array. This green array means that the importance score on these edges are quite large. And for this yellow array, they mean that the importance scores on these edges are very small. And for the figure B, the GN Explainer will assign a node feature mask on each node feature dimension, and then it will optimize the node feature mask. And the node feature with red cross means this node feature has very small importance score, and it's not that important for the prediction of target. So how to optimize the edge masks and the node feature masks? They use the mutual information of the original model prediction between the original model prediction and the masked edges and masked node features. They try to maximize the mutual information of the original prediction and the masked graph, and then use the target to optimize the edge mask ME and the node feature mask MX to find the final edge masks and the node feature masks. And the masks are randomly initialized and updated to the final states. And the final model predictions will be the edge masks with highest top K scores. And the second algorithm is called subgraph X. The target of this algorithm is to try to find the subgraph that has the highest importance score while the graph size is constrained. Because the search space of subgraph is quite huge, we will use the Monte Carlo tree search algorithm to cut the search space of the subgraphs. In the search procedure, the algorithm will cut the node of the graph one by one until the final subgraph is small enough. And how to find which node to cut? We will use this heuristic function, which is the sum of Q and U. The Q is the Q is the reward function of this carding node. That means if this node is card, what is the importance score of the subgraphs with the carding node? And the U means the exploration score. If the next subgraphs has been explored for many times, then the U will be very small. If the new subgraphs has never been explored, then the U score will be very huge. And then with such heuristic function, this search algorithm encourage to find the subgraphs which has higher importance score while never being explored or explored very little times. Yeah, and we will do this search algorithm many times until the state is nearly stable. Until the algorithm doesn't try to find more states. And the final explanation results will be the subgraphs with the highest importance scores. Okay, so for the importance scores, we will use the Shapley value, which comes from the cooperative game theory. To assign the importance score fairly. The original definition is like this. If several players play together to win a game, and they will get the reward for the game, how to assign the reward to each player fairly? Maybe player 1 and player 2, they can't finish the assignment separately, but when they cooperate together, they can finish the task very well. And in that scenario, they have to get a similar reward from the final game win. Although they can't achieve this task separately. So the Shapley value will consider the cooperative game into consideration. And for each subgraph I, and all the possible node combination S, it will calculate the marginal contribution, and the reward of subgraph with the node set S minus the reward of node set without the subgraph, and then consider all the possible node sets, and using a weighted sum as the final Shapley value. And in this way, we can consider the importance scores while considering the subgraph cooperation with all the possible node sets S. And here is a pipeline of the subgraph X. In this figure, it gives an example of how to calculate the Shapley values. The subgraph is node 5043, and the node set, which is also called a correlation, is node 1. And the marginal contribution will be the subgraph 5243 with node 1 minus node 1 without the subgraph. And in the second subgraph, the correlation is node 2, and the subgraph with node 6 is 0.57, and the node 6 without the subgraph is 0.27, and the final marginal contribution is 0.23. And the final Shapley value will be the weighted sum of all the possible correlations, which is 0.45. And we will calculate the importance score in each step of the power tree search algorithms to calculate the heuristic function value to decide which node to cart until the algorithm is converged. Yes. And that's the subgraph X. I have a question. I don't understand why this provide the explanation, why, what kind of explanation gives me better than I just look at the original graph.
The explanation compared to the original graph.
Yeah, so here I think the purpose is to provide the explainability, right?
Yes.
You say you give me all this information, I put on the graph better than I did the original graph.
Yes.
I failed to see that. I couldn't really see
You
how.
can see that in this example.
Okay.
So here we also propose the graph sentiment dataset, which is transferred from the text classification datasets. And in this dataset, each graph is a sentence, and this sentence expressing the positive or negative opinions to a movie. And you will find in the first example, this movie review is a positive review, and the models predicts the review is positive. The subgraph X gives the result that the explanation result is make old store review, which is a positive face. Yes. However, in the second example, the movie review is negative, but the model does a wrong prediction. The model thinks the movie review is positive, and the algorithm finds that the model thinks the terms tuning going to inspire. It's very important. And that's the reason why the model gives a wrong prediction in these examples. Okay.
So the substructure basically tells us what the model will focus on when it does the prediction.
So when you select the subgraph, you have a threshold to say which.
Yeah,
it's
we
not
usually
the scoring
use
you
like
use.
top K important. So
Yeah, for GN explainer is top K, and for subgraph is the size of the subgraph.
How top the K you will choose? So how do you choose the size of K?
Yes, so it's a problem to select the value of K. So to address this problem, we propose some matrix called fidelity plus, fidelity minus, and sparsity. The sparsity is the size of the explanation, the ratio of size of the explanation compared to the original graph size. And we can calculate the fidelity plus is the probability drop when we mask the explanation results. And we can compare different methods in a similar sparsity level. And we will compare the fidelity plus value with similar sparsity level. The similar sparsity level means the explanation size is consistently similar between these different explanation results. And we can also compare them in different sparsity level. And to compare the fidelity plus score of these methods. And here we propose a benchmark of explainability methods using such fidelity and the sparsity score. And we implement 7 different explainability methods from different categories on 6 different datasets, including the synthetic dataset, test to sentiment dataset, and the molecule datasets. Okay. So that's how to evaluate the matrix. In this way, we can compare these methods systematically, and we don't need to worry about the size of the explanation results. We can also compare them.
actually, when you want to use that, it's you to decide what size. It's actually it's like a ranking. So we rank the nodes from the top important to not least important, and you can just take a look at it from the top one, and you can choose any number of nodes you take a look. And as long as you find the top, let's say top 4 or top 5, you can understand how the model thinks from all these nodes, and you will find.
So is that possible? We have a top 4 that means positive, and now we add one more word, it means negative.
Okay, that's possible, I think.
That's not possible if the model thinks so. Okay,
So in general, from those 6 comparison, is the conclusion that subgraph X is the best?
yeah.
Or is the method that has the highest expandability?
It achieves the highest fidelity score over all the data sets.
I know, but then the conclusion is the highest expandability, right?
So speaking of fidelity, you assume you have a ground truth, right?
The fidelity is like the fidelity score is the probability drop when we mask the explanation on the input graph. So we put the original input graph into the model, we have a prediction score, and then we take the explanation results to mask the original graph and take that to the model. We have another prediction score, and the probability drop is the fidelity score.
So what does the plus minus mean?
Plus means that we mask the important components. The minus mean we maintain the important component and mask all the other unrelevant components. So that's all about the lecture part of explainability methods in graph neural networks.
Regarding the case you're talking about, like add a fifth, those like two different, that may mean the explanation model is not good. Yeah, for a good model, where good model, you should not like touch that.
Yes. So I will move to the code part, code demo of the explanability. So here is a code demo of the explanability methods in our DIG package. In our package, we provide the data APIs and model APIs and method APIs. Also, we provide the proposed evaluation matrix in our packages. So I will show some. So in this code example, I will show you how to implement GenExplainer and subgraph X using our package. So first, we will load a dataset. Here we use a synthetic dataset called BA shapes. And we also provide other datasets such as the text-to-sentence dataset, text-to-graph dataset, and the molecule dataset. We call it from the this module is called the synthetic graph dataset, and we give the root path and the dataset name to this class and get the dataset. And then we will load a well-trained GCN model. We have provided some checkpoints in our packages, and we for the provided GCN2 layer model, we will tell the model that the explanation level is model level classification and the dimension for the input features and the hidden feature dimensions and the number of classes in these prediction tasks. And then load the statistic to this model parameters. For the GenExplainer, we can import this class from the dig.xgraph.methods. And then we will give the GenExplainer class the model efforts to optimize the edge features and then rig to optimize the edge features. And whether the task is the graph level classification, model level classification. For the subgraph X, it can be imported from the same module called dig.xgraph.method, and we pass the model to the class and the number of classes, and whether the task is graph classification or the root classification, And also the reward method. Here we use the NC Monte Carlo Shipley value as the final reward method. We can also replace it with other function values such as original Shipley values. And first, provide some visualization. So here we provide a class called plot utils to show the graphs. And this class can plot all the data sets we provided in this our package. And here I give you an example of the synthetic data set. The yellow node means the base graph, and the key motif is the house-like motif, and the green node, blue node, and the red node is class 1, class 2, and class 3. And the reason why the classes of these nodes are different is that they are the house-like motif, and this is the reason for the node class, and also it will be the label for the explanation results. And we first use the GN explainer to explain the original graphs. And the red array means the important edges that contributes most to the prediction of this node. And we can find there are some edges in the house-like motif and some others are not. We will use the visualization graph methods in the GN explainer to plot such figure. And also we can provide the explanation result for subgraph X. We use the function plot utils and using and pass it to the subgraph X explainer dot visualization. And also tell you how many nodes in the final explanation results. And the final visualization tells you that the house-like motif is the reason why the model gives such a prediction. Instead of visualization, we also provide a matrix. We provide X collector, which is used to collect the calculated fidelity, sparsity scores for each examples. And we enumerate all the data sets, the first 20 data sets, examples of this data set, and using GN explainer to explain the graphs and the predictions of this node predictions. And we also use subgraph X to explain the predictions of this node, target node. And then we put the explanation results into the collector and print the final fidelity score and sparsity score of these two methods. That's all.